In the early 1950s, the world's eyes were fixed on the sky. Yet a handful of engineers at General Mills in Minnesota were looking in the opposite direction. Harold "Bud" Froehlich, a mechanical engineer born in 1922, was part of the Aeronautical Research Division. While the public associated General Mills with breakfast cereals, the United States Navy viewed them as experts in precision mechanics and high-altitude ballooning. Froehlich's background in aeronautics would eventually become the unlikely foundation for the world's most famous deep-sea submersible. The concept for a maneuverable underwater vehicle began not with oceanography, but with the Office of Naval Research. In 1958, Alan Vine of the Woods Hole Oceanographic Institution proposed the need for a manned vehicle that could reach the ocean floor for research. Most existing vessels, like the bathyscaphe Trieste, were essentially underwater elevators, capable of going deep but having almost no horizontal mobility. Froehlich was tasked with designing a deep-sea jeep. His initial prototype was called the Sea Pup, a small two-man craft that prioritized maneuverability over sheer depth. Froehlich approached the problem as an aerospace challenge. In the deep ocean, the enemy is hydrostatic pressure, which increases by 1 atmosphere for every 10 meters of depth. To reach 4,500 meters, the vehicle would need to withstand over 6,000 pounds of pressure per square inch. Froehlich realized that traditional submarine shapes, long cylinders, would collapse under such force. He turned to the sphere, the strongest geometric shape for resisting external pressure. The heart of what would become the Alvin was the personnel sphere. Froehlich specified the use of HY100 steel, a high-yield alloy developed for the Navy. The sphere was roughly 2 meters in diameter and 1.33 inches thick. It was designed to carry 3 people, 1 pilot and 2 observers. Unlike previous submersibles, Froehlich's design included 3 viewports made of plexiglass, tapered to fit into the steel hull so that the water pressure itself would push them tighter into their seals. One of Froehlich's most significant contributions was the solution to buoyancy. Traditional bathyscaphes used massive tanks of gasoline for flotation because gasoline is lighter than water and incompressible. This made them bulky and hazardous. Froehlich collaborated with companies to develop syntactic foam. This material consisted of tiny, hollow glass microspheres embedded in an epoxy resin. It provided the necessary lift while remaining structurally stable at great depths. This innovation allowed Alvin to be small enough to be launched from a surface ship. On June 5, 1964, the vessel was officially commissioned at Woods Hole. It was named Alvin, a contraction of Alan Vine's name, though Froehlich's engineering made the name possible. The vehicle was 22 feet long and weighed roughly 36,000 pounds. It featured a unique propulsion system, 3 small propellers powered by lead-acid batteries. The main propeller at the rear could tilt, and 2 smaller props on the sides provided vertical and lateral movement, giving the pilot the Jeep-like control Froehlich had promised. The most difficult challenge for Froehlich was not just getting humans to the bottom, but allowing them to work once they arrived. In the early 1960s, underwater robotics were almost non-existent. Froehlich turned to his experience at General Mills, where the company had been building Model 150 manipulators for nuclear laboratories. These arms were designed to handle radioactive materials with precision from behind a shield. Froehlich's task was to take this dry technology and make it function while submerged in salt water at pressures exceeding 6,000 pounds per square inch. The breakthrough was the pressure-compensated hydraulic system. In a standard hydraulic setup, the difference between the high internal pressure and the external ambient pressure would cause seals to fail or the entire system to implode. Froehlich used a flexible rubber bladder filled with hydraulic oil. As Alvin descended, the increasing weight of the seawater pressed against this bladder, instantly equalizing the internal oil pressure with the external environment. This allowed the hydraulic pumps and valves to operate as if they were at the surface. Froehlich gave the arms 6 distinct degrees of movement, mirroring human anatomy. shoulder pitch and yaw, elbow pitch, wrist pitch and rotation, and finally the jaw for seizure. This 6-axis dexterity was revolutionary for 1964. The arm was powered by small, oil-immersed electric motors that drove a central pump. By sending electrical signals from the cockpit, the pilot could open or close valves to direct fluid into specific cylinders, allowing the arm to extend 72 inches and lift over 100 pounds. Inside the cramped 7-foot sphere, the control interface was deceptively simple. Unlike modern master-slave systems, where a pilot moves a miniature model of the arm, Froehlich's original design was rate-controlled. The pilot used a switch panel to move one joint at a time. It required immense patience and coordination. Through the thick plexiglass viewports, the pilot would watch the mechanical claw as it hovered over a sample, adjusting the flow of hydraulic oil in bursts to avoid crushing delicate deep-sea specimens. Safety remained the primary engineering constraint. If the arm were to become wedged in a rock crevice or entangled in a cable, it could pin the entire submersible to the sea floor. Froehlich designed a jettison mechanism at the shoulder. With the flick of an emergency switch, the pilot could activate a hydraulic cutter or an explosive bolt that would sever the connection entirely. The arm would be sacrificed, falling to the seabed, but the Alvin would regain its buoyancy and return to the surface safely. The true test of Froehlich's design came in January 1966. A United States Air Force B-52 bomber collided with a KC-135 tanker during mid-air refueling. A 70-kiloton hydrogen bomb was lost somewhere in the Mediterranean. The Navy's standard recovery equipment was useless at the depths where the bomb was suspected to be remaining. Alvin was shipped to Spain and began a grueling search mission. On March 15, 1966, at a depth of nearly 800 meters, the pilot spotted the bomb's parachute. Froehlich's mechanical arm was used to help clear debris and assist in the recovery. This event proved to the military and the scientific community that a small, manned submersible was not just a luxury for biologists, but a strategic national asset. While Harold Froehlich eventually moved on to work for Litton Industries, and later as a consultant, his creation continued to rewrite textbooks. In 1977, Alvin discovered hydrothermal vents on the Galapagos Rift. These black smokers revealed an entirely new ecosystem that did not rely on sunlight for energy, but on chemosynthesis. This was one of the greatest biological discoveries of the 20th century, made possible by a machine designed by an aeronautical engineer in the Midwest. Harold E. Froehlich passed away in May 2007. He was a man of technical precision who viewed the deep ocean as a series of engineering problems to be solved. His archives are the thousands of successful dives Alvin has completed over 60 years. The vessel has been rebuilt many times, the steel hull replaced with titanium in 1973 to reach 6,000 meters, but the fundamental layout and the 3-viewport configuration remain as Froehlich drafted them in the late 1950s. Thanks for watching, see you in the next video.